Everybody ready? Raise your hand if ready. It's going to be active attention. You ready? Okay. Look at this. You guys have probably seen something like this before, right? Turn on an LED with an RGB. And isn't that crazy? And almost everyone except the CS major. So let's break this down. What's going on here? How does this work? We can all look at this and go, yeah, that turns on an LED. Why? That's my question. Why? Why does this turn on an LED? Anyone?
Magic?
No, not magic, although it sure looks like it. Anyone? What's going on here? George?
There's a passing wheel on it.
That's highly controversial. Just talking to Leo.
There's an electrical potential across the diodes of the LED causing light to be emitted.
Kind of. That's actually not even at the core of it. I'll just tell you, the brightness of an LED is directly proportional to its forward current. What is forward current? It's the current going forward in the air. So somehow we need to make that current happen because that's what's going to make the LED emit light. In this circuit, we've got 3.3 volts, 0 volts, resistor in between, right? Why? Anyone know? Why is there a resistor there? Why did they set 3.3 volts up to an LED?
Too much current can blow out the LED because it has.
True. So you're saying that a resistor is current limited.
Yes.
Why? Yes, so
The forward current of an LED is exponentially proportional to the voltage across it.
true. So what George is saying is that if we just put 3.3 volts across the LED, we could pretty much rest assured that the current through it would be theoretically infinite and wouldn't actually be the LED just explode. The reason for that is that LEDs are diodes, which means they have a minimum voltage required to have any current flow. That's called forward voltage. Whenever we're trying to achieve a forward current, we can do that with a forward voltage. The moment you reach that threshold, any tiny little bit more voltage and the current starts ramping up. Here's the analogy I use for people. Imagine you have a bucket of water with a hole inside of it, and you slowly start filling up the bucket with water. The moment the water level reaches the hole, the water no longer rises and water flows out of the hole. That's exactly how LEDs work. Nothing, until when you reach that, now current begins to flow. And if you somehow get that water level above the hole, so much water is coming out. That's exactly how LEDs work. So, how do we calculate what resistance we want? How do we get any guesses? We know our goal is to make the LED on. What does that mean? Okay, that means we need a current here. What current do we want? Yes, George?
Well, first you ask how much current do you want to go through the LED. Using that current, you can calculate the forward voltage across the resistor that you need to match the current.
Yes, exactly. So the LED, as a physical property of it, has that hole in the water bucket, that height, that's called the forward voltage. So let's say in this case it's 2 volts. If we know that we want 10 milliamps flowing through the LED, and we know that when the LED is on, it's going to be 2 volts across it, that means the voltage across this is going to be 3.3 minus 2, so which is 1.3. So we just say, okay, V equals IR, 1.3 equals 10 milliamps times R equals 1.3 divided by 10 milliamps, and you get some hundreds of ohms. And then this works. You hook up 3.3 volts, the LED turns on roughly 10 milliamps going through it. Here's the thing. In the one wheel, this doesn't really solve our problem because we don't have 3.3 volts. We have up to 84 volts. Emphasis on up to, the input voltage is always different, which would mean we have to be, well, new resistor. Every time the voltage changes, we have to do that math over and over again. So we need a resistor that changes. How do you do that? Any ideas? How do you make a resistor change? Jay?
A potentiometer.
Potentiometer, it's a good idea. The thing is, the potentiometer wouldn't die because current for like a headlight is too large. Maybe not really easy potentiometer to do that. But then you'd have to be in there manually turning it when you know your battery voltage is changing, that would work well. How can we make it automatically change its resistance?
Automatic potentiometer. That has logic.
What do we call that in real life? Any takers?
Transistor?
Oh, freaking resistor. You're on fire today, George. You know what you're talking about. So we need a transistor. What kind of transistor? Well, let's just pick the simplest kind, an NPN transistor. All you guys, don't worry about it. If you don't know what that is, don't worry about it. It's a transistor. So here's the rough circuit I set up. We've got all these LEDs in series. You might be thinking, well, series, I've never seen that before. Well, why do you do them in parallel? That's how everything else in the world works. Well, here's my thought process. I've got almost 100 volts coming out of this one battery. Well, why would I want to regulate that down to like 3 volts for a bunch of LEDs in parallel? So it's a huge amount of current flowing through them. I just put them in series. Super high forward voltage, very little current. Adding more LEDs does not increase the current. They're in series. The current goes through all of them no matter what. So in this case, I have 9 really nice 6-volt LED modules, which is a forward voltage of 54 volts. So as long as my battery voltage is more than 54, we can turn it on. But we need a resistor, and that's what this guy is. It's a variable resistor. For those of you that haven't taken an electrical engineering class related to transistors, don't worry about it. But for the people who have, this is going to make a lot of sense. How do you control the current through an NPN transistor? You guys know like the 2 equations for an NPN transistor? Oh, Jay. You know them, Jay? Do you remember that?
It's like V overdrive squared.
No,
times.
stop. No, not that one.
Not that one?
Yeah.
It's not that one.
It's linearly proportional to the current going from the gates to the collector.
The base of the
Base.
yeah, so I think what you're looking for is that the current going out of the transistor down here is equal to some variable beta times the current entering the transistor here. The second equation is that the sum of this current, and this current, or sorry, sum of this current equals this current. Like the currents are coming together and all going out. So what we get from that is that a very, very tiny current coming in here can result in a very large current coming out here. So, okay, fine, we can put a current in the transistor that makes the current go out. How do we make sure that it is regulating the current? So no matter what the input voltage is, there's going to be a constant current going through it. What I did is, this might look a little weird to you, but I have this Zener diode. It has a reverse breakdown voltage of 1. So that means the voltage here, no matter what is here, is going to be 1 volt. And ignore this for now, because this is a wire thing. If I assert that 1 volt is here, and also another property of BJT is that the voltage from here to here is 0.7, that means the voltage across this is 0.3. I now just asserted that the voltage across this resistor, no matter what this voltage is, will be 0.3. I can now set the current. I will say, okay, 0.3 volts. These resistances will result in these currents. The universe solves it for me. I told the transistor this is the current I want. Thank you. And it does it. What do you guys think? Any thoughts? Any thoughts about this? Any concerns? Looking good? Everyone's okay with this? Everyone's on board? Yes, George?
What happens when one of those LEDs blows up?
It turns out.
The whole thing.
The whole thing turns out. That's what's, yeah. It's better than it catching on fire. Yes, Leo?
So in this setup, it's just a fixed current no matter what.
Fixed
Stuck
current,
with it.
yeah. Well, this is related to possibly making the less. We're going to talk about that later. All right, guys. So yeah, we're good. We're going to go for it. You guys are on board with this? All right. Let's see what happens. Oh, sorry. This is what it looks like in real life. Good. Yeah. Cool LED bar. Look at those beautiful LEDs. Oh my gosh, they're so big. Nice little driver. Pretty great. Okay. Now let's see how it works.
Wait, no, why am I saying? Why are you doing this with a live battery?
Okay, go. Do it. Oh! This is the minimum setting. Let's keep that in mind. Is it warm at all?
No.
That's the big chip. Touch it.
Okay, go, Danny, go.
Oh my god.
Oh, it's hot. It's cooking. It's cooking. Oh, it's cooking. Oh, fuck, wait. Why did it get bright like that? What? Dude, it was at 99C. It was? Yes.
It was?
Yes.
Danny, are you ready? I have to change forever, and hopefully a good way.
Bro,
Don't check your connection.
wait. Yes. Good. Okay.
No shorts anywhere?
No shorts.
Nothing's touching anything else?
Hold on, wait. One more check. Good. I just don't want like flames to shoot back out my head. Because that's happened so many times.
What? Okay, now turn her on, turn her on.
Please, God. Oh, yes. Yes, bro. Yes.
Turn it off, turn it off.
That's awesome.
You're right, Danny, that is. So, it worked pretty well. In fact, that whole system is in his one wheel to this day, right?
Still works, yeah.
Which is awesome. That's the thing, though. You guys notice problems in that video? Same thing, yeah.
You were eating food in the main space.
That was before, that's a year ago. That was before you had that rule.
Yeah, that's right. We've got it in the last 6 years, actually.
Oh, really? Okay, then yeah, that's wrong. Anything else electrically wrong?
Well, won't the transistor get very hot eventually, the resistor?
He said 99C, but I don't know if you noticed the video. It was 115C in a second. That transistor was not doing okay. So the reason is that we've taken this huge voltage and outputted a smaller voltage to achieve the target current we want. Where's all that energy going? It's a resistor. It's sizzling there, dissipating all that extra energy to heat. That is not good. So what do we do? It's brainstorming time. What do you do? What's the big idea? How do we fix this? How else can we do this? Right? Okay.
Add a cooling system.
Cooling system. It was already thermal pasted to a massive heat sink, and it still got too hot.
Oh.
Any other ideas? Maybe a complete architectural shift to something else, perhaps? Yes?
You could use pulse width modulation to lower the effective voltage.
Pulse width modulation. So let's see, what's Leo saying? He's saying, instead of having it on all the time, let's turn it on. Turn it on. Turn it on. Turn it on. Super fast. And the proportion that it's on compared to the proportion that it's off is going to result in an average current between off and fully on. And that will appear to us as dimmer, and it will appear to the circuit as a less average power loss. Here's the thing though. Even if we do that, that circuit is still limited with the maximum current that it can drive. So that's still like that. We're wasting so much energy and heat. That is crazy. But you're on the right track. We can use time to our advantage. How exactly? What else? We're going to use pulse width modulation, but I'll give you a hint. BJT is not going to cut it. We don't want a variable resistor. Remember, someone remind me, what does the resistor do?
Limit the current.
It limits the current. How else can you do that? Without a resistor, perhaps. Something that limits current without dissipating the energy. Perhaps you can think of some kind of electrical device that converts electrical energy into maybe not heat, but something else. We can then take back afterwards. An inductor. I'm amazed that you just said that. That is exactly right. Oh, what? So yeah, we're busting out the iPad because we need to figure out a new solution. So let's do it. Okay, so what are we gonna do? So somehow we need to make it so that we can take the battery voltage and say, okay, LEDs, you get 0 battery, 0 battery. And then an inductor on the outside limiting the rate of change of that current. How do we do that? With something called a half bridge. So I'm just gonna draw that. So we've got a new kind of transistor here called MOSFETs. So the BJT, to achieve a current through it, you have to put a little current into it. MOSFETs don't care about current. If you put a voltage on its gate, then that will control its resistance. So in our case, we just want the MOSFET to be fully on, fully off, meaning as low resistance as possible and then as high resistance as possible. That's called using it as a switch. So I don't know if you guys have ever seen a circuit like this. Let's say we have like 3.3 volts, some resistor. Let's do our LED thing again. We put a MOSFET right here. The way you turn a MOSFET on is you put a voltage on its gate. Just kind of like how the LED has a forward voltage where it only starts doing stuff once you reach a certain voltage. MOSFET works the same way, it's called the threshold voltage. If the gate voltage is less than the threshold voltage, MOSFET's off, it's like open circuit. The moment you reach that threshold, it exponentially decreases its resistance towards 0. So what we want to do is put the voltage on the MOSFET between 0 and some number sufficiently larger than the threshold. So it's like on, off, right? And so in this case, it's super easy to achieve that voltage because you can just take like a microcontroller and say, hey, output a signal, right? That's easy. Here's the thing, though. When we're doing this half bridge thing, look, we've got 2 FETs stacked on top of each other. If we have a microcontroller over here, and we try to send a signal here, all good, right? That's just like over here. Where it gets tricky is if we want to send a signal here. Because when this MOSFET turns on, this voltage goes up. It goes up to around here, I'll just call this AS. That means that this is way bigger than this, which means that the voltage is now smaller or severely negative. We need somehow that microcontroller signal to lift up with that high side FET as it turns on. Does that make sense to everyone? Is there any confusion on that? Good, that's good, yes, George?
So one of them is a P FET, the other is an M FET.
No. If it was a P-channel MOSFET, then we could be like, okay, go floating, and then the resistor pulls it out and makes that super duper high voltage, what's the word? High voltage tolerant microcontroller. And then when we want to, we pull it down to ground. In this case, so P-channel MOSFETs are worse than N-channel MOSFETs. We want these MOSFETs to be super duper exactly identical. So when we're switching on and off, it's like the same figure. What we're doing is it's still an N-channel MOSFET, but when we turn it on, we need to somehow keep a voltage on its gate that lifts up with it. What you do to do that, it's a method called bootstrapping. And what it means is you have a little capacitor that you charge it up right here. So when this MOSFET turns on, that capacitor is all good. It's holding that voltage there. And then when you want to turn the FET off, you have something reconnect here and like suck the voltage out of the capacitor and it turns off. So it's like a flying power supply. This capacitor is just there just to hold the voltage on that FET. This whole thing is crazy. Like it's a crazy circuit that is used all the time because half bridges are super, super commonplace in power electronics. So you just get a chip. I got a chip called a half bridge gate driver. It has all the logic. You just get it 2 PWM signals. It'll convert it to 1 for the low side, 1 for the high side. It has the diode built in, because you need a diode, so it will instantly drain into your supply. And it, all you do is give it a capacitor. You say, oh, here's that capacitor, you're good, and it works. That took a long time to actually figure out how to do that, because there's a lot of specifics about how big it does the capacitor need to be, because like how fast they switching, stuff like that. I'm gonna spare you the details because we're on a time crunch, but that's the general idea, right? Okay, pretty cool. I think we're done with that. So, for the first time ever, I used LT Spice to simulate something outside of class. Isn't that crazy? I needed it. Good thing I said DC65. This is a basic little circuit here where I have this thing simulating our half bridge, outputting high, low, high, low, high, low. Fed inductor, capacitor, and then our LED with a little 1 ohm resistor, and then just to smoothen that slope out just a little bit. And the simulation results were like, yeah, looks good. Probably should work, maybe. I don't know. I don't know if my simulation was good or not. So we immediately have another question. Where do we get these signals to turn these FETs on and off? For the BJT, it was pretty easy. We used like linear math to just make the circuit assert that what we want it to be true. In this case, we now need two PWM signals saying, high side FET, turn on for this long. Okay, now turn off low side FET, turn on for this long. Because based on that duty cycle, we're going to achieve a different output. Right? Like with a really low duty, going from here percent. Really low duty cycle, on average, going from low to high, it would be on average around here. And if we had a really high duty cycle, we have around here. We need something to figure out what voltage we want to get our target current, right? And the idea is what does that? How do you do it? Is there some analog way? How do you output a PWM signal based on some kind of logic? Some kind of like
Microcontroller?
a microcontroller, exactly. We need a little baby computer. We're gonna like measure the current. Go, oh, it's too low. Increase the voltage. Measure the current. Go, okay, now it's a little too high. Decrease the voltage. Right? Makes sense, right? It's a little computer. How do you tell a microcontroller what to do? It's just a little chip. Exactly, George has it. Here's the thing though. I'm not programming this thing with Arduino. The very first slide said safety critical system. Arduino screams not safety critical system. Those things be whack. That's what I say. I've also used a bunch of companies' proprietary frameworks for programming microcontrollers. All bad. They just are bad. I don't like them. George showed me this really cool thing called libOpenCM3, where it's like all Cortex M processes. You can use this unified API for controlling all stuff. It's still bad. I realized that C is fundamentally fast. Normal C++. You know what we need? Rust, baby. It's time to rust, guys. This is crazy. We're about to spend the next, what? At least 5 more minutes. Talking about Rust. Making this so easy. So easy without sacrificing performance and maximizing safety. This is safety critical. We need it to be safe. So how does Rust do this? Still, okay, fine, we're going to program out the Rust. What does that mean? I read this straight out of the 196 presentation because I teach this. This is a microcontroller. What does that even mean? Danny, do you even know what a microcontroller is?
I don't know what microcontroller
Exactly.
is.
Well, it's a CPU with some memory, with some clock, with some peripherals. Okay, what the heck is that? CPU, everyone pretty much can understand. It computes stuff. You give it some math, it spits out the answer, right? Makes sense. You give it instructions, it'll compute stuff. Memory, it's how you record things. Record things that you want to compute later, so, whatever. It's just a way to store information. Clocks are how you do things with time. How fast does the CPU compute things? How fast does the memory retrieve information? And then we got this weird thing. Oh, I forgot about making the shimmer. What's that? It's like a mouse keyboard. What is that? It's actually the same idea. A mouse and keyboard is how you interact with your computer. The microcontroller, peripherals are how the CPU interacts with the world. So what is that exactly? Well, things like this. Serial communication, cool fancy signal outputs, measuring the real world, and then just general interacting with stuff. We also have flash if we want to persistently store information when we lose power. And timers directly use clocks to do any kind of timing stuff we want to do. So cool, look at this little toolkit we've got to just do pretty much anything. This is why microcontrollers are everywhere, because they have everything that you possibly need. So how can Rust tell these things what to do? Well, that's obviously with code. But what kind of code? Let's take a look at this. So we have two PWM signals, right, for these FETs. I don't know if you guys have thought about this, but what happens if both FETs are on?
Done for.
Done for. Because it's shorting the battery. Percent battery through the top FET, through the bottom FET, ground. There was nothing there. We just connected the battery to ground. That's not good. We don't want that, of course. So we need the PWM signals to guarantee to be opposite of each other or both zero. Does that make sense to everyone? Opposite meaning, so okay, I feel like I didn't make this super clear. The one PWM signal corresponds to one FET. Other PWM signal corresponds to other FET. We need them to be like this. Or like, every yeah.
Can you go back to the picture and demonstrate why both of them would be a good idea?
Yeah.
Or just not go backwards? I will do that. So, I felt it was oh, but not.
So this is our battery. We got a big old battery connected like this. If this is on, it's like a wire. If this is on, it's like a wire. That's a short circuit. These FETs shall never be on. Not yet, if you understand and agree with that. Great. So how do we guarantee that? I could write code that says, all right, pin A, turn on. Then pin B, turn off, in like a huge for loop. That's crazy. CPU is going to be active constantly going. We don't want that because we have what? Peripherals. They can do jobs like this for us. So this was the first thing I ever did with embedded Rust. That's when we put Rust on an embedded system microcontroller. I knew that I could instruct the microcontroller to output what's called complementary PWM. And so we have multiple PWM signals where one is always the opposite of the other. So that's called two channels. So you can configure the PWM peripheral to just do that. It has the ability to do that. How does Rust, being a programming language, know how to control peripherals? Rust has no idea what a peripheral is. Well, some very smart people made a tool that parses the manufacturer's specifications of microcontrollers into Rust. It's called a peripheral access crate. So a crate in Rust is like a library or a package. So it automatically says, okay, we know this region of memory, if you put a bit here, does this thing in this peripheral. Remember how in my diagram, peripherals are also connected to memory? That's how the CPU can make the peripherals do stuff. It just puts just the right bits in just the right place in memory, and the peripheral reads that. It goes the other way, so that peripheral can put some bits into memory, and the CPU would go, oh yeah, thanks, I got that. So what this is crazy. I manually looked at the datasheet. The ST datasheet is like, okay, you gotta enable these 20 things. Then set up the thing, and then finally enable the thing. And then it'll go. This took me forever to figure out. All these lines are saying, this region of memory, put in some bit. These names refer to bits in certain positions. Like for example, let's look at one that's like easy to understand. This one, I'm saying this pin is floating. Then I say it's now an output push-pull. And then I say put it in alternate mode, and then say the second alternate mode. It's crazy wording, guys. You don't need to fully understand it. Just understand, I configured a version. Check it out. Look at that. The orange signal is channel 1, and the blue signal is channel 1 and for like negate the not of it. That was crazy. I just made a microcontroller do my bidding just by putting some bits in the just right places. Here's the thing though. That sucked. Did you see that? That was like 100 lines of code from PWM. It shouldn't be like that. And so above PACS, peripheral access grids, we use something called a HAL, a hardware abstraction layer. So what abstraction layer beyond that? People don't want to be manually putting bits into memory. They should be able to just say, oh, I want to make a PWM thing on these 2 pins, right? Or I want to make an output on this pin, just like you do in Arduino, right? Well, Rust has you covered. We have a HAL. And look, it's so easy to say, okay, here's my channels. I want it on P8, P7. Make PWM with those channels. Extract the channels from PWM. Set them, enable them. And it works. Here's the thing though. When I first got this HAL, they didn't support confidential PWM. So I had to add it to it. This is the first pull request of today. I contributed to this public Rust HAL repository basic complementary channel support, which is sick. So now it's super easy. No one has to like learn all the stuff I had to learn on converting with this. They just say PWM, put it here, done. And it does it. Figures out how the abstraction layer. That's your cost abstraction layer. So that's very sick. So what do we get from this? Our first new design from the first hot one. Now what do we have? Microcontroller. Sick. What microcontroller? F0. Why? Because I heard of it and it was cheap. Next thing, gate driver. This puppy does this super cool thing where we just give it 2 PWM signals and it will output 2 PWM signals specifically for each FET. There's our bootstrap capacitor, which keeps this FET working when it's on the high side. Random capacitor stuff, output inductor, output capacitance. We've got a half pitch here, guys. And what's this? Oh, look. This is called current shunt. Because, of course, if we're trying to achieve a target current, we have to know what the current is in order to make adjustments. So that's what that is. We're saying, okay, we know its resistance, we measure the voltage across it, now we know the current through it. That's how you measure the current. There's some cool little amplifier here that converts that to a nice voltage for us to read. Plug that into the ADC on the microcontroller and box it up. Should be pretty easy, right? Well, let's see how this one went.
All right, and we have 82.3 volts.
Okay, here we go.
No.
Oh, it's brown.
Shit. Dude, I got that on video, dude. What's something that?
I don't know why that happened, but
Forensic analysis will reveal it.
so last video, I plugged the battery into the cell and it shorted it. That's not supposed to be ground. That is supposed to be VS. So I plugged in this one now. Let me just quadruple check that this is VS, but it is ground. That's what okay.
Here we go. Test 2. Yeah. Dude, okay. Okay. Oh. 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 All right.
Hello everyone, welcome back.
So this is tip 3.
Take three, let's just take three.
Take one, we shorted the battery to itself. Take two, we just didn't plug it in. And take three, we're gonna see if we can plug it in.
We did not plug it in because this connector get in Tokyo melted.
I'm just gonna hold it.
Oh.
It's fucking.
Plugged in. Really? Am I somehow still? Oh my gosh. I'm just gonna pretend. Let's just assume it is. I mean, what do you want me to do? I touch the thing and.
Oh, yeah, wait, don't try.
Stand.
My turn. To be wearing a garage.
How?
The fuck?
Wait, is this one broken too? No.
I say it's not. Okay,
That's not
okay,
good.
okay.
Okay. Take four.
Take four.
Again, we did not actually plug it in.
So,
This time we definitely for sure are.
oh, it's in. Wait, it's in?
In, bro.
Holy shit, and it's not on fire? It's not good.
I don't know.
We're entering the compression age of this project. Over the course of the next 2 or 3 months, I lost my mind in the vision, trying to get this darn thing to work. I made like 4 of them every time, some new reason it wouldn't work. I literally went crazy. So, let's see, the next, yeah, first problem. I used the wrong footprint, the main part of the chip, the most important chip. They look pretty similar, they're not. They look it. So I don't know how that chip ever turned on, ever, because it like clearly these pads don't line up. So yeah, that was the first problem. The next slide, no. So there were a lot of problems. So I eventually realized that like this footprint thing was causing a problem in that video where I was like, I don't know. And eventually I was like, okay, screw this chip, screw this whole thing. I went straight for high density. I don't know if you guys noticed, that's a tiny little rectangle PCB. Everything is really small. We kept not knowing if it was working because we couldn't even touch the multimeter to pads because they were so small, it's so high density. So I was like, okay, I jumped the gun. I'm making a huge pro-ribbon board that's just covered in stuff. Surely I'll figure it out. It also did not work for various reasons. Something I realized was that I forgot a very important thing, which was a capacitor on the input of the application. I don't know if you guys thought about it, but when those FETs turn on or off, the rate of change of current is insane. Where's that coming from? Not the supply, that's all the wires go to. We need a very localized source of charge to draw from. That's why you need capacitors on input. The result of not having them is crazy oscillations. Literally, I plug the board in and it go, like it would make the sound, and then it would just shut off. So finally, I realized that. The reason it took me so long is because this system is so high frequency that when I'm thinking about like voltages propagating around this thing, it's like molasses sloshing through a tube. It like takes the time like matters. So when I was plugging these dinky little capacitors that Vision had into it, they weren't doing anything simply because they had legs. Those legs instantly just removed the benefit of the capacitor. Those legs being like half a centimeter long was too long. That's a high frequency. We're dealing 300 kilohertz here. So eventually I realized that I could actually just solder another SD capacitor. Thankfully, the layout made it possible for me to do that. And so I did it. We got this.
Powering these LEDs with this power supply, rapidly changing the input voltage and look. It adjusts the duty cycle to keep current constant. Look. The brightness is literally constant. That's rust, baby. 100% rust. Oh, yes. Yes. I'm turning off the light. It's so bright. I can't even look at it. Holy shit, they're so bright. I'm so scared to touch this. I need to feel it's warm. Ow, pretty warm. I'll increase the dead time. Oh my God. Am I with that right now?
So, pretty dope. They turned on. But I don't know if you noticed, that waveform had a little lump in the front of it. My oscillation convention measures were not even close to over. Great. I added the absolutely necessary capacitance on the input, but now there's a lot of very sensitive work to make that waveform nice, straight, right? We're going to talk about that. So I don't know if you guys, that video actually really well showed what we're talking about, this whole PWM thing. The height of that waveform was our input power supply. I was like, and the goal of my board was to make it such that the average voltage on the output remains constant. So that's why when it got taller, it also got thinner. And then if you think about it, the area under that waveform was remaining constant, because that means the energy throughput is remaining constant. Does that make sense to everyone? That's the feedback loop. So that whole thing of it moving when I was changing the height of it, code was doing that. The rust was saying, we got a new current. It's too high, decrease the duty cycle. So, right, and that's why the LEDs were remaining at a constant brightness, the currency maintained. Everyone understands that, right? We're all following that? Okay. New design.
That is sick. That is sick.
I understood finally after months what was holding my circuit back. And with my newfound knowledge, I put it in a pretty new package. So that big old board wasn't working because it was big. Isn't that crazy? These circuits are so high frequency, you have to really squeeze them, be really small, and make sure that the path the current takes is going to be okay and not affect other things. Look how cute this little board is. So nice. That's the gate driver, these are the two FETs, and that's the microcontroller. Pretty simple layout, right? There's like 4 things. On the underside there are the passives, like the big old capacitors, the big inductor, etc. So I actually learned how to do this from a really amazing TI technical document explaining how to properly lay out butt regulators. That's what it says, it's a butt regulator. And they talked about how you need to make sure that the current loops are sufficiently small, because the bigger the area of your loops are, the more it is an antenna. That's exactly what this was. An antenna. Check that out. That's bad. Here's the thing though, improvement, the frequency of the oscillation is really high. It's 85 megahertz in this picture. So you'll notice this is a new oscilloscope. That's because on my analog discovery, it looked like a square. I was like, wow, I did it. Why does it keep exploding? It was so high frequency, my oscilloscope had no idea what was happening. What's awesome, guys, this is my first ever radio. I made it on accident, but I made a radio. So what's going on? We have a perfect layout. Nice little loops. We have the input capacitance. What else is there left to do? Why is it oscillating like this? Any guesses?
You mean low pass filter filter at the high frequency?
So you're saying snubber. That's what everyone on the internet said. That is absolutely not what you should do. The snubber gets so hot because it is on the output. So it's going 84 volts, 0 volts, 84 volts interval, 300,000 times a second, that capacitor explodes. That's not the solution. We shouldn't need that. You know what it was? It was going to sound crazy. It certainly sounded crazy to me when I figured it out. My circuit's too good. You know how we have that nice gate driver? Those really nice FETs? They turn on and off so fast, like picoseconds fast. The universe is not okay with that. When a voltage changes that fast, even just the wires are now inductors and capacitors because it's so high frequency. So even though my circuit was like the physically smallest it could be, the universe does not allow something to switch on or off that fast. Sick. I now know that I have technology to make things switch at reasonable speeds that are way bigger. Because these are really tiny. That's why they're able to switch so fast. So I just put a resistor on the gate for the MOSFET. That makes it turn on slow. Because the gate of a MOSFET is like a capacitor. So if you just have a capacitor that's super low, it instantly charges. But the resistor there is a slow charge. Resistor MOSFET. It's like an RC. Super cool. That fixed it. It's just good. What is the next slide? Oh yeah. Okay. Great. We did it. We made the smart wave. Okay. We made it. It works now. Okay. Good. We got it. Now, what is the control? The loop? How? What is the code for making it know what to do when the current just is wrong? Right, here's what the slide wants to do. Wait, no, this slide wants to do that. Look, here it is in my point. Great, right? It's in there. It's in there. Now we're saying, okay. You guys saw the hardware. You guys understand how hardware works, but we have to write code to like do what should that be? Karcher, your controls guy.
Come on, Karcher.
What should we do?
Oh, of course, PID.
PID, are you sure? What if I told you all you need is an I? Isn't that crazy? Here's the general idea. It's iPad time. Yeah. So, everything dealing with computers is finite, right? We cannot have infinite precision in anything. Everything has to be finite. That goes for time as well. We're doing PWM at some frequency. How many duty cycles can we have? In our case, 300 kilohertz, only 160. You know what that means? There are only 160 voltages we can output. But to achieve a target current, you may want a voltage in between two of the voltages we can output. Right? Does that make sense to everyone? So, for example, let's say for some point in our system, the LEDs, in order to achieve the current we want, really want to be at this voltage. This voltage will result in the current we want. But the only two closest duty cycles will give us this voltage or this voltage. Which one do you pick? That's a trick question. You pick both. You just pick both for certain amounts of time. See what I'm saying? Since this one's a lot closer to the bottom one, we should probably be at the bottom one more of the time. So you end up averaging, just like what we were doing with the PWM in the first place. We're PWM. Yes, George? That's exactly what I was going to say. Perfect. Okay. So how do you implement that? My first naive approach was, okay, we're going to make a whole thread that just is a loop that sets the duty cycle back and forth between like the proportion, and then it's going to like add up. That's crazy. You see a PID loop. What is the I in the PID? Who knows? What's the I? You know.
Integral.
Integral. What that means is, as an error exists over many time steps, we accumulate that. So hey, the error is building, we've got a big old error here. So consider if we're at this bottom voltage. The error will very slowly be negative, right? like that. And if we were at the top, it would very quickly rise because the top is much farther away from the target than the bottom. The eye term just does this. We set a maximum error, which basically means, okay, the eye turns out of error. Oh, it reached a certain error, change the news cycle. Okay, it's out of error. Oh, it reached a certain error, go back. So eye term just naturally will take different amounts of time depending on how far away we are from the target. Did that make sense to you, Carlos? Whatever. You get it. Whichever one is farther away will be after less time because of something. That makes sense? Okay. Let's see what that looks like though. You know, drawing it can only get you so far. Let's see what that actually looks like. Here's real life. So as I change the power supply voltage, these two lines are moving. And it is solving for whatever proportion between them results in our target voltage. And it's just great to watch that. Right? So as the line moves up, it starts using the bottom one more, then it moves back down, it starts using the top one more. And this results in a super smooth looking LED. Because this is running on 8 kilohertz or something, we can't see that. If you got a super slow camera out, you see the LED go back. You know, but we can't see that. This is just how light dimming works in general. You just go back and forth between two lights, and it works great. Just an eye. Who'd have guessed? No P, no D, just eye. Pretty cool way to hack PID with doing one. Okay, what's next? Oh yeah. Any questions? Okay, guys, this is where.
Is this time for questions?
Sure, yeah, anytime there's a question.
Why do you need such fine-grained control of the current book with the LEDs? Like, why do you do this PWM, not PWM?
Because if we didn't, the light would flicker. So let's say we just said, whatever, pick the duty cycle that's closest to what you want. Then it will discreetly jump to the next one once it's closer. Is that what you're saying? Is that what you're saying?
Sure, I mean, I'm guessing we have like some finite set of brightness levels.
Yeah, exactly, yes. And that's why we were jumping between the two adjacent ones. But if we don't jump between them, we just go to the closest one, you'd see that as the battery voltage changes, the light would get brighter, brighter, brighter. Like you'd see it step between them, right? You see what I'm saying? If you jump between them, it'll stay looking like constant runs. Does that make sense?
Sure, I didn't see it at first.
Okay. That's actually what my first firmware version did. They just picked the closest. So that, like, well, yeah, think about it, there's two possible voltages. We're here, so we're good. But if these slowly start going down, it's still picking the bottom one, and then each halfway it goes now at the top. You get a little bit like discretely switch it, and that's visible. There's only 160 volts. And since it's an LED, only the top like 50% of them are found, because all of them is up below 4 voltage. So yeah. What's up with the triple question marks, guys? That means we've got a big problem on our hands. We've only had single question marks before. You know what I'm about to say. Okay, fine, Adin, you can achieve a current to make it some writings. What if you want it to be a different writings? What if I'm on my one wheel, and I'm like, oh, it's daytime, I don't think. Turn it off. How do I do that? It's like, I'll give you a hint. That's going to take us an hour. It's crazy. First thing that pops into your head, an app somehow that like talks to it somehow. Hey, well, how does a phone talk to anything? I guess is how you talk to something from. Yeah.
Bluetooth?
Bluetooth. Totally. Everyone knows what Bluetooth is, right? It's how you interact with peripherals. There's that word. Peripherals. So STM32F4, which is the microcontroller I used, unfortunately does not have Bluetooth capability. But have you guys ever heard of Arduinos? They have Bluetooth. I want to use that. So the way Bluetooth works is you can advertise services. In my case, the service is headlight. And it has various characteristics like target current, current temperature, current target, all those things. And the phone should be able to just read values from it. pass send values to it. But then we have this teach meter that knows all this stuff. How's it gonna tell my headlights that? Welcome to communication. It's crazy. It took me a long time. But basically, here's the general idea. We're gonna represent any kind of like message as a command. Command is like, change the brightness, or the command would be tell me the current temperature, right? And so in Bluetooth, we'll have a characteristic for each possible command that can be sent or received. And then it's going to turn that into a serial signal that goes across two little wires inside it. I'm pretty sure I have a picture of that. Yeah, here's the little guy sitting here. These two little wires, you guys know what a UART is? A lot of people here know what a UART is. Super easy way to do asynchronous communication. So this guy can send it from the Bluetooth signals. Here's the thing. This is safety critical. What if something happens across this medium and I see a bunch of like jarbled bytes? What if those bytes say, crank it up, crank it to max? That's gonna kill something. So, first axiom. Receiving and executing invalid commands is unacceptable. How do we ensure that we never do that? Any guesses? Call it checksum, which is a common way to refer to a CRC check, which is where you basically compute a very chaotic polynomial from some data. So like if the data's changed a little bit, polynomial is completely different. So you receive your data and a CRC, and then you read all the data and you compute the CRC that matches the CRC you received. Good. You got the data. There were no errors. It doesn't. That means there was an error somewhere. Don't know where. It's actually impossible to know where. All we're doing is a CRC. Okay, guys. This is the part of the presentation where we open actual code and actually look at it. Are you guys ready for that? Are you guys mentally prepared for that? Yeah? Everyone's ready? Okay. Here we go. It's going to be pretty nuts. So, well, let's open up Zen. Wow. This is the firmware for everything. Okay, we're going to spend some time here. Let me pull up the chair. This is going to get pretty crazy. So, first thing we need to worry about is just at all, we're doing Rust here, right? How do you tell a Arduino to do Bluetooth? That's like, sounds so easy, but it's like, how does Bluetooth even work? So far, we've been like putting bits in places. Bluetooth is like crazy on top of that. Well, here's how it works. NRF52 is the chip inside of the CPU. The company Nordic that makes that chip has an SDK for using it. And they have this little binary, it's closed source, that does all the Bluetooth stuff. Problem is that the SDK is in C. You know I'm not going to use that. So some very smart people developed Rust bindings to the closed source binary that handles all the Bluetooth stuff. That binary is called the soft device. It's this thing Nordic made that knows how to do Bluetooth. You can just tell it how to set stuff up and get events. So you just flash that closed source binary, use this Rust library to get bindings to it, and you can do all the Bluetooth stuff. Here's the thing though. When I looked into this, I learned that this Rust Bluetooth library was based on something called Embassy. Embassy is a Rust script that allows you to do, you ready for this? First class async stuff on a bed. I can define functions that are async. I can await things. I can have multiple threads running concurrently, exchanging information in real time. The performance overhead is close to zero. Close to zero. In many cases, actually, it's faster than doing it yourself. And that's because they leverage something called DMA. That stands for direct memory access. You know how I said peripherals have access to memory? They really have access to memory. A CPU can just tell the peripheral, do the thing. The peripheral can go, do all the stuff, put a bunch of information in memory, tell the CPU, done. And while that peripheral is doing that, the CPU is going and doing other stuff. It doesn't need to worry about that anymore. Tell the peripheral to do it. It can tell other peripherals to do stuff. This is how async is possible on an embedded system with just one CPU. Tell the peripherals to do stuff, and when the peripherals are done, they tell the CPU to turn down. The CPU can immediately start doing stuff. So let's look at the Bluetooth code. Here's all the firmware. It's split into 3 sections. Common, which is code that's shared between the NRF chip and the headphone. Oh, I think I can. And I'll even close this. A lot of files. Okay. Is that better? A little bit more, maybe. Like that? A little bit more. Is that good? Close this too. So the fact that I have code here that is common to both of these devices is nuts. These boards don't even have the same CPU in them. And I'm just writing code in one spot and they're referring to it in the same spot. There's code in there that you guys will be like, there's no way you put that code in there. Because it's just, you think it's impossible for that to be common between these 2 devices. But first, let's just focus on the Bluetooth. Step 1, do Bluetooth, right? I have this nice file, it's called BLE. So I can just define my service. Look how nice and declarative this is. We have a service called the headline service. Here are the characteristics. So the phone will just see these. It can say, here's a value for that characteristic. Say, give me a value for that characteristic. It's just like a value store. That's just like, just holds values. It's like over-the-air variables, basically. And look how easy this looks. There's some stuff in there you don't need to understand yet. But I just tell it, okay, here's the ID for this. You can write to this, and it can notify the phone. Notify means the phone can just be sitting there chilling, not doing anything, and suddenly it goes, oh, I just became aware of a value for this. It didn't even ask for it. This device can force it on it. It can send in a notification. That's how that works. Pretty dope, and like it's pretty easy. We just like handle Bluetooth events. That's it. It's like not that bad. Like where is it fit? If we get a write to the request characteristic, we take it. We got a write to that one, we take it. Look what this is. Here we have a type called request that deserializing from the data we got. Okay, here another type called control deserializing from the data we got. I wonder how that works. We'll get to that later. First cool thing I did, here's the next PR. I can't believe that this was public, but the way you configured advertisement data, you guys know like a Bluetooth device, like when you're looking for Bluetooth devices, you like see it pop up, it's like it's name. That's an advertisement. You're not connected to it, you just can see it exists. It's called an advertisement. I have to configure that. The way they had it for you to configure that was you just make an array of raw bytes and just read the documentation to know what bytes to put in there. That's crazy. That's so easy to abstract. So it's actually not, it took me a week. But I did it. Look at this. This is our advertisement data. I called it ABV data. Here's the flags, here's the service UUID you're advertising, here's the short name. And then once you're connected, if I scan more information, here's the full name. Wow. That was easy to understand. It just kind of says what it's doing. I don't have to make raw bytes every time. But guess what? If I hover over this, it says it's equal to an array of just bytes. Where did those come from? I made something called a procedural map. Yes, Jay. I know. Procedural map. Jay went. So this is the first superpower you get with Rust. I wrote code that writes code, procedurally generated from the code you get. So I realized the process for generating these bytes just by reading the Bluetooth spec. It was like, okay, I can make a thing that just generates this for me. And so the reason hovering over it shows you the value is because this value is what's called constant. Throughout the entire duration of this program running, it does not change. It's the same. Advertising data is always the same. You know what that means? Why should I write code that computes this, that runs on it? That's a waste of time. It never changes. The compiler can compute that for me. That's exactly what procedural macro is doing. It's coercing the compiler into computing something it was never designed to compute. And generating this for me. We have new PR. I didn't make an animation for it, but new PR achieved. Pretty cool. Now, let's go back to what we were looking at here. Anytime we receive, the phone has written a value to a characteristic, we take those bytes and make the command from it. So like these are some commands you guys like get done. If the phone wrote something to the request characteristic, it sent a request. And we made a request type from that. Is that like, you guys kind of follow that? How does it know how to deserialize some bytes into that type? Any guesses? Did I just manually say, okay, the first byte is this value, then first byte and the second byte bit shifted as the next value? That would be literally nuts. The moment I tiny little bit change the type, oh, all the deserialization code broken. So guess what I did? Well, let's look in common, because the commands are common to both of them. Let's look for requests. Oh, there it is. Well, I don't see any code. I didn't write a function called deserialize or serialize. Wait, but what's this? Derive, serialize, deserialize? Are you seeing this? I just marked it as, yeah, you can serialize it, deserialize it. Where's that code coming from then? That's right. I made another procedural macro. This is but one of many procedural macros I made for this. Procedural macros are so cool. This is an extremely mundane process. Every time ever you say, thing, whatever. It's so annoying, it's so fragile to implement that yourself. Because the moment you make a tiny little change to some type, you can do the whole thing over again. It's just pleasant. What's so cool is I can actually say, cargo span. Wow. And if we scroll up here, let's look for request. Wow, look at that. So let's make this big. This is the code that my procedural macro generated. Look at that. It implemented serialize. Here's what it looks like. That would have sucked for me to just write myself every time. Any tiny little change, oh, you gotta do it all over again. Let's look at deserialize. Wow, this one's not so bad, but still, God, there are so many things that need to change when you change any little thing about the type. Is that not annoying for you guys? Like, that's the coolest thing ever. The code is doing my work for me. I made a tool that just does the work I don't want to do for me every time. I'm going to use this forever in the future. Also, here's the best thing. It's a zero cost abstraction. It's a popular thing amongst the Rust stations. Why is that? Well, let's think about an example type. Say I make a type called foo. It holds an unsigned 8-bit integer and unsigned 16-bit integer. If I get an array, that's obviously going to be of size 3, because it has to hold 3 bytes for a 1 byte and a 2 byte bit. How do I know how big that array is? Well, when my procedural macro looks through all the types inside of it, it says, oh, the first type, I know it's this big, it's U8, that's size 1. The next type, well, it's U16, I know that's size 2. So it just adds those at compile. It's called constant evaluation. How does it know which slices of the array to extract for each type? It just, again, at compile time, adds up those sizes together and just hard codes those locations. The reason I made this, Rust serialization and deserialization packages exist, but they have a runtime process. They don't do all that fancy static analysis. They just iterate. Did we get there? Yes. Okay. Continue iterating. I don't have time for that. This is running in an embedded system. I have very few clock cycles at my disposal. I don't want to compute things I already know. So that's why this is. So this is great because the moment I receive bytes on the UART, I just say, oh yeah, you see that? Boom, I got a command. Every command implements execute, which means you can say command dot run. How do I know that? Well, let's Let's see what it looks like when I receive a command with the command reader. Let's see. Well, for the NRF, we're just going to say reader. Okay, on the Bluetooth board, here's what it does. We say reader. When you receive something, here's a bundle. What's that? We'll get to that in a little bit. Then we get a command from the bundle. We say, if we are connected to Bluetooth, and if running it, do not return an error. Okay. Wow, that was great. Wow, any command ever just works in this. I can make a new command right now, and this code wouldn't change. And it has completely new capability. Who do I sound like right now? Yeah. So that's pretty cool. Okay, but surely sending a command, that must be hard, right? Because there's so many different commands we can send. Let's see what that looks like. It's even shorter. All right, so this thread, this is a freaking thread, by the way, sits here and awaits a new command to send. So this thread is showing here sitting, not taking up any resources. The moment someone somewhere who knows pushes a command to the command queue, commands to send. This guy says, great, got it. We're going to send it. Here's a write about send. Like that, the simplest mode to follow in the world. It's so clear. It's so awesome. It's so expressive. So what's this bundle thing, though? Well, so here's the problem I faced. Look at this. This queue clearly holds a type. And every date has to have a type. But we can send like a bunch of different commands, and each command is a type. So how do I make it one type? There's a bunch of commands. How do I do? Well, I just make a type that holds all of the types. I call that a bundle. And I made another procedural macro that just generates bundles for me. Here's what they look like. The first bundle are commands from the headlight. The headlight can send us a status. It can send us a control saying here's what the current control settings are. It can send us a monitor command, which has like temperature, duty cycle, measure currents, stuff like that. And it can send us what its config is. The config is like stored in Flash. Data that persists, the configuration of the headlight. That makes sense. What can we send to the headlight? We can request information. We can set a new control like the brightness. We can send a new config. We can send a reset, tell the reset. That's pretty basic. That makes sense. Nice. Now, what's the type of that queue? One of these bundles. It can hold any command because it's one of these. Each bundle holds a command. Does that make sense? I feel like it might not make perfect sense because I have not taught you all Rust. So probably the notion that a type can hold one of these types at any given time is strange. But that's whatever. That's okay. Learn Rust and then get back to you. So this is all pretty good. What time are we at? I can explain more or just in about 3 minutes. Code stuff? Okay. What's one other cool code thing I can explain? I think it's in 5 minutes, about 30 minutes ago. So let's look at the actual process for ingesting a command. So that's going to be in the reader. So this thing is crazy. Oh my god. I love this function. Remember earlier we were talking about the CRC? Or that whole thing? When did that happen? Well, let's look at this. This loop, look, it's trying to parse a command. This means we have received bytes. And it's now our job to say, hey, we got a bunch of bytes. Is there a command in here? And we always have to be certain. Because we remember, we said it's unacceptable to run invalid command. First thing we do is we read ID. I have some cool fancy code here that lets me iterate across the buffer and extract types from it. I say, okay, first thing is need an ID. An ID indicates what command is sent. Then I say, okay, read the CRC. That should be the next byte. Then it's just read the bundle. That's it, you read 3 things. It's cool though. How does Rust know that ID is a type of weight? Where did I say that? Does this function return weight? Well, no, because we're using it. You can't see it, it's being used in here too. I'm also going to return a bundle. So how does it know that? It's crazy. Rust is so smart. It's because we use IDP right here. And this type expects like you can. That means this must be a like reversed back up. It's like, oh yeah, that I know that. That's a UA. Just cool stuff like that. This is just such a nice, simple little function. I think I don't have enough time to go over like all of this, but trust me, there's like 3,000 more awesome sections of my code like this. I don't know why I'd ever use C or C++ again. This code is so easy to understand, is so like robust. I can just plot. This is platform agnostic. I get an NRI53, I get an NRI51, I get an STM32, I got an ESP32. The code does not change because embedded Rust has this big interface where everything has to conform to this, no matter what platform it's on. It's just beautiful. The last final cool thing about this is that all of these commands, you'll see that some of them are marked with this, derive, unify, something. I noticed that all this fancy stuff, like right now we're saying, okay, yes, the headlights and the Bluetooth chip have to both know about these commands. You know what else has to know about the commands? The app. That's not even Rust though. I made an app in Swift. How does it know? This generates a Swift package, compiles a Rust binary, embeds it into a Swift package. And now in Swift, I have access to all of the types, all of the functions. And so in the Swift app, I can also just say control, deserialize, control, serialize. I don't need to write it again. It's all there. The moment I update the firmware, the app is updated. Oh my God, that's like crazy. It's doing, again, I got a tool to do the work for me. Work that I technically could do, but would be fragile. What, you want power?
Your Mac is dying.
My Mac is dying?
Yes.
Oh, that's easy. So, there you go. You guys get it. It's cool, right? Pretty crazy, right? You guys done with Rust now? Is that enough Rust? No, not enough. Yeah, it's enough Rust. Okay. Well, thanks for looking at the Rust. Okay. We're back in the presentation. So, we got that all working. So, oh yeah.
I'm really sorry, but we have to be going to something.
Oh, okay, don't worry about it. I think the presentation's I think it's over in like 5 minutes.
Intermissions.
Right. Yeah, I think we're at the end. That was the last thing I was
We have
talking
another
about.
3 hours.
Just get next quarter, right?
Right. So after I got this all
That was
working,
awesome.
I went down to the forest and having this image. It's like I put a car headlight in my automobile. Look how many trees we can see. That's crazy. Then, oh yeah, that was the night where I accidentally exploded my Arduino, and I called Jordan. I was like, Jordan, I need a Arduino right now. And he's like, wait, I'm not know, but my brother might be at my parents' house. Here's my parents' address. I got it. Then I went out to this forest, and it worked.
Dude,
So-
that is
so-
insane.
Yeah, what's so cool is because
What happened last night?
yeah, that was 2 minutes.
Oh, yeah, that's right.
Because I use Rust to statically analyze all of these tiny little independent components in this whole thing, it worked first try. When have you ever written a C++ program in the first try? I never. That doesn't happen. And it's because it was all statically analyzed. I knew it worked. All the 3 different pieces of hardware shared the same code. I couldn't accidentally make them use different code if I wanted to. It's not possible. They reference the same code. And that's what you get. You get something that's safe code. Well, I didn't show you, I have like a ton of cool Rust things that make it super safe. Like, it will, at compile time, say, this branch is possible. We won't compile. This branch is unsafe. Stuff like that. Here's what we got. Big old headlights.
Looking smooth, yeah.
Thank you.
All right, yeah, thanks, guys.
Dude, that was an awesome.
And great job. I'm really sorry. I really gotta run.
All good, no problem.
Awesome.
Great.
I have plenty of time if you want to do another hour.
Dude, hey, that was awesome, bro.
So, do we all agree we should?
W stream. Wait, and do you have anything else to say to the stream? I mean, learn Rust. Rust or bust.